Hi, my name is Erini Lambrides, and I'm a third-year graduate student in the Physics and Astronomy department at Johns Hopkins University. And today I am going to talk to you about how me and my advisors and my collaborators answer the following question. How do growing supermassive black holes regulate galaxy evolution? So, one of the main goals of galaxy evolution is to be able to describe and quantify and explain the incredibly diverse array of galaxies that we see in the universe. So if we were to put into a model a prescription for how the universe evolves in terms of structure formation, and the relationship between normal and dark matter, and run a simulation from just after the Big Bang to the present-day universe, the galaxies at the end of that simulation are way more massive and way more luminous than the present-day universe galaxies. Now, the bulk of the luminosity from a galaxy, and a normal galaxy, is going to be coming from the star formation processes, stars. So something must be preventing star formation that is not currently accounted for in the models that I just described. Now, what could prevent stars from forming? Well, if the gas and dust that stars form from are too warm, stars won't form. And if the gas itself is expelled, stars won't form. Now, in almost every single galaxy that we've looked at, we see a supermassive black hole in the center. And the gas and dust on the outer edges of that galaxy is gravitationally blind to the supermassive black hole in the center, yet properties of the supermassive black hole scale with properties of the entire galaxy. So this implies that maybe the evolution of one affects the evolution of the other. Now, when a black hole is actively growing, it's the short-lived period of time that's emitting a lot of excess radiation into the plane of the galaxy. And this whole engine, this very efficient engine of converting matter to energy at the center of a galaxy due to the accretion of matter onto a supermassive black hole is known as an active galactic nucleus, or an AGN. And maybe it's this AGN that is supplying the energy that is imparting onto the gas and dust that forms the stars, affecting it, and thus quenching star formation. Now, the problem is finding actual statistical evidence of differences in the gas and dust that form stars in galaxies with an AGN in them and galaxies without an AGN in them is difficult. So my first few years at Hopkins, I worked on this project, which was basically characterizing the warm gas and dust in active galaxies and comparing them to the gas and dust in normal galaxies, or galaxies without an active galactic nucleus in them. And this was work I did with Professor Nadia Zakomska and a couple of collaborators. And so we aimed to look at the molecular gas in galaxies and find or see if there is a statistical difference in their properties. Where this molecular gas is emitting in the electromagnetic spectrum is in the mid-infrared. And in the mid-infrared, it's a beautifully rich area of the electromagnetic spectrum for galaxies, because we're not only seeing the effects due from star formation, but also from the AGN. And there's a host of molecules and atoms that are emitting in this region. So in this slide here, I'm kind of showing a cartoon on top of an actual image of a star-forming region, a photodisassociation region. And in the center, what you're seeing is this dense star cluster. And this star cluster formed from a big molecular gas cloud. And after those stars formed, their UV radiation kind of carved out a cocoon within this dust ball. And that yellow line is where we have the front. And further in, what we're going to be seeing is excited molecules. And what we're really looking for is molecular hydrogen, because that's tracing the bulk of this gas, and dust, which we'll be probing using polycyclic aromatic hydrocarbons. Now, molecular hydrogen can be excited by star processes, shocks, X-rays, and we hypothesize AGN. If the AGN is impacting the molecular hydrogen, that'd be pretty sufficient evidence that the star-forming gas and dust of a galaxy can be affected by an AGN and potentially explain why stars aren't efficiently forming. So the way that we do this is, first, we are going to measure the dust. First, we're going to measure the dust. Then we're going to measure a region of the mid-infrared spectrum, which shows how active the central accreting supermassive black hole is. And we're going to see how does the molecular hydrogen change as a function of how active the black hole is. Now, because the molecular hydrogen is also affected by star formation, we need to take out the molecular hydrogen emission that is due to star formation processes. So we do that. And we find how, as the black hole becomes more and more active, the amount of extra molecular hydrogen emission not from star-forming processes increases. Now, this is a result that has been found before, but with such a large sample, our sample is all of the extragalactic objects in the largest repository of mid-infrared spectra, so from the Spitzer Space Telescope. We really see the portion of the parameter space quite clearly where AGN are the most active. It doesn't really tell us anything about the physics of what's going on with the molecular gas. Now, molecular hydrogen is incredibly hard to observe. Even in galaxies that have a lot of molecular hydrogen emission, the actual signal to noise within the spectrum isn't going to be that high, especially for the higher transitions. So because we have such a large sample, in fact, the largest repository of active and non-active galaxies with mid-infrared spectra, we're going to use all the information we can, even from the bad detections. And we do this by constructing a hierarchical Bayesian model. And I'm not going to go into detail about this, but the paper link is in the YouTube description, so I encourage you to take a look. The conclusion of that, though, was we found an over 200 Kelvin temperature transition in the highest transitions between AGN-dominated galaxies and AGN-not-dominated galaxies. So what this is saying is that there's a population of molecular hydrogen in galaxies with an AGN in them that is hotter and that exists in a larger quantity than in a not active galaxy. So this is the first evidence of really finding a different population of the molecular gas, one that cannot be explained due to star formation processes. And so we're really excited by this because this is really pointing us in the direction that there can be statistical differences between the gas and dust. And it is within this that perhaps we can then explain maybe how the AGN is coupling its energy to the interstellar medium of its host galaxy. And so the thing I'm going to leave you with is, where is this population coming from? Where physically is this getting excited? Now, there are many different ways that people postulate that AGN could be imparting their energy onto their host galaxy, different modes of them interacting within their environment. One of those ways is to have a radiatively driven wind that sweeps through the galaxy. And as it's sweeping through the galaxy, it is picking up all the dust and gas that's in its way. And maybe dust and gas is even forming within the swept up materials. We think it is there in this swept up materials or formed materials that we're having this extra population of molecular hydrogen emission. This is Erini Lambrides, and thanks for watching.